is this. Again, this I1, by our definitions, is the first strength invariant. And again, in the chapter of the stress, we also have the stress invariance. The first one is defined by sigma 11, sigma 2, tau 11, okay. Tau 11, tau 22, and tau 33. Again, this is what we call the first stress invariant. And this is called the first strength invariant. Okay. So we keep this in mind. Then from here, are you able to see? Let me do this one here. So tau 11 equal to, let me copy that one, equal to 2 mu plus lambda epsilon 11, and tau 22 equal to 2 mu plus lambda epsilon 22 and tau 33. I simply copy from the matrix, okay? 2 mu plus lambda tau 33. Okay, that's the relation we expanded here. So from here, for the first one, you can see basically is this. Tau 11 plus tau 22 plus tau 33 equal to how much? I simply, based upon this, I take the summations. Okay, so from here, the left-hand side equal to this number. Basically, this is I1. The right-hand side equal to this number, and that is 2 mu plus lambda and 11, 22, 33. Is that right? No.
So are those the C, the compliance matrix, or what's going on? So C
lambda. Hold on a second.
Or tau.
This is the. Sorry, I missed something. So here is lambda 22 plus lambda 33, right? And this is lambda 11 plus lambda 33. This is lambda 22 11 plus lambda 22. Good. So the right hand side, adding those things, that should be equal to 3 lambda plus 2. If you do it carefully, so this is the right hand side, and the right hand side equal to this one here. The left hand side of this summation equal to that side here. So basically here the first conclusion is this: I1 equal to 3 lambda plus 2 mu, and this one. What this means. This one basically I want to introduce is this one is related to what we defined as we call the bulk modulus. And I'm going to explain this right away. In engineering, how we define the bulk modulus, and that is basically is like this. For simplicity, let me take the cube elastic model for explanations here. Assuming we immerse an elastic, for example, soft elastic cube into the deep ocean. Okay, under there they will substitute a uniform hydraulic pressure. Okay, again, I use this model for demonstration. So uniform so that means the tau 11 equal to tau 22 equal to tau 33 pressure, negative stress. So let me say negative sigma. Okay, for example, hydraulic pressure, that is the magnitude sigma, for example, sigma is whatever. Let me say P. P is the pressure there. Negative, that means compressive. Okay, so from here we know in this way our I1 equal to simply minus 3P. Okay, on the other side, when this object is under compression, because that is elastic, it's under compression, it's going to shrink, right? And it's going to shrink, that means its volume is going to change. Okay, so here I'm going to calculate this one. The change in volume due to the submersions into the high pressure, okay? And how do we calculate the change in volume? The change in volume basically can be approximated by this. Let me assume, this is a unit of the unit cube, okay? So that means for this side, for one side, before deformation is 1, and after deformation its length become 1 times strength times original length, which is 1. So that is the deformation. This is the side deformed after the loading. Good. So one side is changed by this. The second side is changed by that. The third side is changed by this. Okay, epsilon xx, yy, zz, xx, yy, and zz. Okay. So this is the change volume minus the original volume that representing is, the 3 multiplication representing is a deformed volume. Deformed volume minus the original, that means change in volume. And original volume is 1. Okay, so these calculations, you can see once you expand it, this is a normal strength, assuming that should be very small. So if we ignore the higher order terms, basically this one approximately equal to epsilon x plus yy plus zz. This is our I1. Okay. So for our bulk modulus, we define as the K. The bulk modulus, by definition, is this. That is the engineering definition. That simply is this: is change the volume rate, okay, divided by the magnitude of the loading. Now the pressure is in this magnitude, compressive. In nature, this number is negative. So artificially, we put a minus here to get everything positive. Good? Okay. So under these situations, you can see basically this one, delta V over V, that calculation is I1. And minus P in our calculation is how much? Is I1 divided by 3, right? So from here, you can obtain P equal to this number here. Okay, so basically this one by our calculation is 3 times I1 divided by I1, and that one, I1 divided by I1 is this one. So we can plug in, so that is equal to 3 and 3 lambda plus 2 mu. So this is our engineering definition of the bulk modulus. Again, bulk modulus defined is by the rate of the relative change in volume rate compared to the pressure. Be good? So for example, I'm older to all of you here, and your effect rate, the ratio should be less than mine. So I'm kind of more spongy in my body. Right? So if we come to say the swimming pool, say if all of us able to dive down to say 20 feet, 20 yards down to there, then you will see the change in my shape will be more significant than yours, right? So that means in that case, if this number is larger than compared to the same loading, then the bulk modulus associated with mine will be bigger than yours. So that is the very quick comprehension of this number here. Okay. So today we stop here and then get a few more very useful information I'm going to summarize and come back Wednesday. Okay.